Hi class, we continue our study in chapter 10, moving into section 10.2 for our last topic in this section, which will be about surface areas. Okay, so suppose the curve C is given by the parametric equation, so x is a function of t, y is also a function of t, and t varies from alpha to beta, okay, where f prime and g pi are continuous, and g of t is also greater than or equal to 0. So what we're doing here is we're rotating this about the x-axis. Okay, so we want to find the surface area, and we take this curve, rotate it around the x-axis. So if c is traversed exactly once as t increases from alpha to beta, then the surface area here is just given by the surface area is equal to the integral from alpha to beta, 2 pi times y. Remember, y is a function of t, though, times the square root, and if you remember, this is just the arc length, dx dt squared plus dy dt squared dt. So it's just a formula, okay? So the general symbolic formula is s is equal to the integral 2 pi y ds, and s is equal to 2 pi x ds are still valid, but for parametric curves, we just use this ds is equal to this arc length part we saw. Okay. Just follow this formula. Let's do one example with this. All right, so let's just show the surface area of a sphere of radius r is 4 pi r squared. Okay, we want to show this. Okay, so the sphere is obtained by rotating the semicircle given by these parametric equations. Okay, x is equal to whatever the radius r times cosine of t, y is equal to r times sine of t, and t is going from 0 to pi. All we're doing is taking this and rotating it around the x-axis. Okay, so all we're going to have to do is follow this formula right here. All right, so when we do that, just plugging into the formula, all right, surface area is equal from 0 to pi, okay? 2 pi times y, well, remember y here is r sine of t, square root, going back, dx dt squared, dy dt squared. Well, dx dt, here, the derivative of this is minus r sine of t. The derivative of this is r cosine of t, and we're going to square these. So you just have to clean this up. You can see what you get when you do underneath the radical. Well, this is great because what is this equal to right here? Well, that's just equal to 1. And then the square root of r squared is just r. So then r times r gets me r squared, which I'm just going to pull outside the integral. So this integral is just 2 pi r squared, the integral from 0 to pi sine of t dt, which just integrates as minus cosine of t. And when you plug in the bounds of integration pi and 0, you end up just seeing that this is 4 pi r squared, which is what we thought it should be. So this formula works, and just like in the previous lecture on arc length, generally the hardest part about this is figuring out how to simplify what's underneath the radical, and there will always be either a trigonometric identity to use or an algebraic way you can tackle that.